Good morning to all. This means, this session has been being recorded. So, okay. So since it's 9:36, I'm going to share screen to October 6th class first to review what we did last time. Your screen sharing stop share. So nothing there. So we wrote down the derivatives of, let me just, we got up to that point, right? So I'm going to copy this portion. So let's close that one. New share. Okay. Let me print this one here. So we had done this something like this last time. And in a similar fashion, we can take the derivative of the what's called tan inverse x. So say if y equals, let's copy that. Arc tan x, then x equal tan y, and the derivative of tan is sec square. And sec square y, if you remember from your, good old childhood days, is tan square y. So, which is equal to, what am I going to do? Hugh, David, and Precious. Stanko and Precious. Hey, nobody else. Chat. Can you go up? No. Just maximize them. Do you mind recording? Didn't help. From A, didn't everyone? Okay. Okay. So that would be equal to 1 plus x square, because x is tan y. That means dy dx, which is, what is dy dx? ddx of tan e, this one we do. Let's copy whole thing. Control C. Where did the pencil go? Yeah. Come on here. No. So here we are. After that, we got tan inverse x equals, and this will change to 1 over 1 plus x square. Okay, so we get rid of the square root sign. delete. Is that right? Yeah. And we need to get rid of this one also. Okay, so 1 over 1 plus x square. And in a similar fashion, you can show that derivative of cot inverse x would be equal to with a negative sign. Same argument, since cot inverse x plus tan inverse x equal pi over 2, sorry, possibly I copied only this one. Okay. So I have to make changes here. Cot inverse, tan inverse, cot inverse, tan inverse. Okay. Equal minus 1 over 1 plus x square. So we got a list of, in case you want to know what is the derivative of the other ones is, I'm just going to write that down. Okay. So the derivative of sec inverse x, which one will be the easier to work with? Maybe this one. Maybe the okay, I'm going to just say similarly, you can show these following results. Using the derivative of sec x is sec x tan x, you can show that okay, so let me make some changes. So this is first one is sec inverse x or arc sec x. And this would be, okay, make it cosec inverse. Okay, don't look at these are not the right numbers. Okay, you have to change this one. What did I do? I put some new one there. So, okay, never mind. Okay, so start with this one rather. X times square root of x square minus 1. Get rid of this junk. And we have x times square root of x square minus 1. And yeah, chat. Good day, sir. Okay. There is a minus sign here. Did I get enough? Okay. Okay, so open, close. Okay, square root of like this. That does look good. Okay, to me. Okay, so let's see. First, let's check it out. Yeah, it came out right. So copy that one, put it here. And there is an example to get rid of that. Okay, so we got the derivative, derivative of sine inverse x, cosine inverse x, tan inverse x, cot inverse x, sec inverse x, and cosec inverse x. Okay. As you notice that if you put a co in front of it, any inverse trigonometric function, the derivative will be negative of it. That's it. Easy to remember. So derivative of cosine inverse is negative of the derivative of sine inverse. Derivative of cot inverse is the negative of the derivative of tan inverse. Derivative of cosec inverse is the negative of the derivative of sec inverse. Okay. Okay. Some people like to put an absolute value in x. For the moment, I'm just assuming x is positive here. Okay. But some people like to put absolute value. Actually, that's most probably the right thing to do. But at the moment, I'm just leaving it alone. Okay. So this is if x is bigger than 1 for these two. Bigger than 1, suppose. If x, of course, for sec inverse, if x equals 1, there is no derivative because the derivative becomes infinite. So derivative doesn't exist in that case. And similarly, for x equals plus 1 or minus 1, the derivative of sine inverse and cosine inverse do not exist. We have those things. Those are for the derivatives of the inverse trigonometric functions. Now, we can graph these functions properly, but you possibly already seen those functions earlier. We are only taking derivatives here. So you can calculate the derivative of lots of interest. Remember, we can also write sec inverse x as arc secant x, tan inverse x as arc tan x. Okay, they are same. Some people prefer to write arc tan instead of tan inverse. But we will do this kind of things. Okay, so we have done that. We learned how to. So, for instance, if we're going to do a problem like find dy dx, where is it? Find here. Find dy dx if y equals tan inverse of copy. But in this case, suppose we put in parentheses x3 plus 7x plus 5. Oh, sorry. Go back. Maybe it's not a bad idea. So if, for instance, we have this function, y equal tan inverse x cube plus 7x minus 5. And we want to calculate the derivative of it. We use chain rule. Okay. No, I don't want that. I don't want to do that. I want to do this. I want to do. Yeah. Shall I put a square root, but it's too complicated possibly, but one can do it. I mean, if I had to do it, we can do it. We can just write down using, derivative of tan inverse is 1 over 1 plus whatever that quantity is, times the derivative of inside. So we can say derivative of this equals, okay, so the derivative of tan inverse is 1 over 1 plus whatever this thing is. Remember, so we will use chain rule. Derivative of tan inverse x, 1 over 1 plus x square. So instead of x, we will write x cube plus 7x minus 5. What happened? Something funny is happening. I don't know. Let's backspace. I backspaced, I went back somewhere else. Oh, here it is. Here it is. Sorry, not backspace. Backspace like this way. Okay, so it will be the 1 comma 1 plus in parentheses this thing square, parenthesis closed, and times the derivative of inside. So this is what we got so far. Okay, here is what we have, multiplied by the derivative of inside. What is the derivative of inside? 3x squared plus 7. Instead of writing it outside, I'm going to put it on the numerator. Okay, so on the numerator, something is happening. Somebody's, taken my, I have to get rid of this kind of junk. Somebody is fooling around with, I got it. Yeah, this is done, this is done, this is done. Here it is done. So on the numerator, we are going to put 3x squared plus 7. Okay, so in one line, I just wrote down derivative of inside is 3x squared plus 7. Derivative of tan inverse is 1 over 1 plus whatever that u square say. So that is what we call this one u square, 1 over 1 plus u square times du dx. So that will be the answer. You can just write it in one line if you like. So that was one problem we did. Let me see, what was there enough space? No, there was not enough space. Okay. We have several things to learn. And one of the thing is, let me go back. A very important section called related rates. Okay. So we are doing derivatives of inverse function. We will look at related rates and a section called Newton's method. And then we will be ready. Now, should I do the Newton's method first? No, let's do the related rates first. Okay. Related rate is basically an application. So this is the word, what you call the word problem. So just application of what we have learned. Okay. So basically, actually the next chapter is called applications of derivatives. But related rate problems are actually using the chain rule. If you know the derivative of, okay, so suppose suppose t is the independent variable. I mean, most of the time what happened, t equals time. Suppose, t equal to, t stands for time. You don't have to often define it. We'll just assume that is t. Suppose t's time is the independent variable. And suppose we have several variables which are dependent on t. That means changing with respect to time. Let's x, y, z, etc. Whatever, thing is. And suppose y equals f of x. Some function. And suppose y equal f of x. If y equal f of x, comma, then using our, chain rule, dy dt would be, we're taking derivative with respect to time, wherever, dy dt would be, I have to change this one. Equals f prime x multiplied by dx dt. That is chain rule tells us that. Rate of change of, just to explain the chain rule. Sluggish. Why is it sluggish today? Because somebody is So dy dt would be f prime x dx dt. Okay, derivative of f of x with respect to x times the derivative of x with respect to time, because we are taking derivative with respect to time. So that is basically chain rule. That is nothing new. Okay, but we will come to do a problem. Let's take a simple problem. Suppose suppose a circle is expanding. Okay, a circular shape is expanding. Okay, its radius is increasing at the rate of, say I'm going to use inches here, 0.1 inch per second. At what rate is the area increasing when the radius is, say, 10 inches? So very straightforward question. Okay, so imagine that circle is slowly increasing like this way, because it's a small circle, it was growing, becoming larger and larger circle. Its radius is increasing at the rate of, say, 0.1 inch per second. Or it may be changing at a different rate, but at the instant when its radius is 10 inches, it was increasing at the rate of 0.1 inch per second. So I'm not saying that it was increasing at the constant rate, but the area will not be increasing at a constant rate, as we will see. So whenever there is a word problem, this is what you do. Okay, first of all, you define your variable. You may not define t except for the unit. So we will say let about defining your variable. That's the thing. First thing you start with. R equals radius. You can call it x if you like. Destin. No, not that. This one. Thomas, not yet. Okay, let me check quickly. 16 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Whatever happened. Okay, never mind. So let R equal radius at any time. Okay, R is a function of time because R is changing. And A equal area. You can use your anything you like. It's your choice. What letter you use to denote it at any time. Okay, A is the area at any time. What is the relationship between these two primary variables? Also, okay, so our radius in inches, you may like to define the unit also in inches square inches. Let's write square inches in words, otherwise it's confusing. T equals time. You don't have to T. I will always assume T is time. So you don't have to, but except for what unit you're using. So I'm going to use the unit seconds. So we nice clearly define what our variables are and what unit I'm using in case there is more than one unit involved. Okay. So with that, first order of business would be get a relationship between your primary variables. Primary variables in this case is R and A. Sometimes you have to introduce intermediate other variables like some angle theta or some other kind of thing, just to get the relationship between A and R. Well, we already know what the formula for area of a circle is. It is pi r square. So where are we here? No, they're not that one. Okay, undo. I forget that. Yeah. Okay. How many of you, let me just stop share here. How many of you know that formula that I just wrote? Are all of you aware of that formula? A equal pi r square? Area of a circle equal pi r square. I know this, right? Most people say I know this. Okay, but how many of you, I expected that. How if you know a proof for that result? Well, we will show you, I will show you a proof later on. Let's go back to our table, October 6th class, October 7th class, right? Okay, so once we wrote down the A equal pi r square, we use this formula. In this case, instead of y, we have A, and instead of x, we have r. So we get dA dt, okay, equal derivative of this with respect to r times dr dt. Okay, so that means we get, let me copy that thing and change the variables. Okay, here. So we have capital A here, we have capital small r here, and instead of the derivative would be 2 pi r. Okay, put a 2 there. Anthony Barbieri entered. Okay, let's check. Was he here already? No. Barbieri, no. So Anthony, Thomas, Anaya, Luis, those are the ones. Let me see. Okay, so we get this thing. I'm going to hit this button, and this is our relationship. dA dt equal to pi r dr dt, right? But before that, I also write down what I know. I know that the radius is increasing at the rate of 0.1 inch per second. Okay, with our units, r measured in inches, time measured in seconds, it turns out to be dr dt equals 0.1, right? Because radius is increasing at the rate of 0.1, and dr dt is the rate of increase of r with respect to time. That is what it is. So we know dr dt is 0.1. So now we can plug in, put an end. Okay, so when the radius is 10, I don't have to put unit because I've already included the unit there. When r equals 10, dA dt equals you plug in numbers, 2 times pi times 10 times 0.1 equals 2 pi. Okay, which is approximately equal to, but you don't have to, you can just leave the answer as pi, 2 pi, but it is approximately equal to, I don't have it here, approximately to 6.2832. So we can say finally as our answer, at the time, at the moment, the radius is, try to give your answer in plain English also, okay, is 10 inches. The area will be increasing. At the rate of, did I get a T? Yeah, I got the T. At the rate of TE of 2 pi square inches per second. Or you can write 6.2832 square inches per second, but I'm going to just write 2 pi. And instead of writing like this, we can write like this. So that's the rate at which the area will be increasing. The radius is increasing slowly. Every second, it increases by 0.1 inch. Very, very slowly is increasing. But the area is increasing by so many square inches per second. Oh, sorry. Yeah, that's the area, right? I'm sorry, my mistake. That's the area. Okay. So that's an easy problem for related rate. So in this problem, generally, taking the derivatives is not the difficult part. That's the easy part. Often, it's not very complicated derivatives. The difficult part most students feel is one. This is the one, big one. It's a word problem. And I don't know why people get scared by word problem. Are you scared of word problems?
Isn't 2 pi r the formula for circumference?
Okay. John Wayne Mindo, do you think that you have problems with word problems? I mean, generally you prefer, oh, if you ask me, just define the derivative of tan cube x plus 3, I'm happier. Let me see what chat says. Sahidat, I don't know the proof. Okay, yes, because the words make it more confusing. Okay. I didn't write okay. Who did okay? Oh, I didn't possibly hit the okay button. Okay. I don't like word problems. Okay. So, okay, so that's what we have to handle first. That is one reason people are generally scared of word problems. Number two, that is the difficult part, apart from the phobia of word problems, unnecessary phobia, one may say, because it can be hard to find the right equations to use. Okay, David says that. Okay, so how do I address the first problem? First, you have to understand the problem, read the problem carefully, make sense of it. So imagine that in your mind, like the previous problem we did, there is an object like a circle, a circle is growing, like a bacteria culture, and it is growing. Okay, bacterial culture is growing slowly, and the radius is increasing by 0.1 inch per second. Okay. Imagine that in your mind. That's the important part. Also, everything that you learn in calculus or any algebra, trigonometry, etc., you have to internalize it. That means it's not like something mathematicians do, something, etc., but you feel it yourself. If you cannot apply it, you have learned nothing. If you cannot apply your knowledge, it's nothing. You learn nothing. You cannot do anything with it. So anything, when we say it is a rate of change, try to imagine in your mind what it means, not just some gobbledygook they talk about. So that's the important part. And once that is over, you will find that word problem. I mean, honestly speaking, after coming to this country, I finished my master's in India. I was doing some research. I came to this country. And then especially when I'm, actually even in Cornell, when I was PhD, doing my PhD, I was the teaching assistant. So there were a lot of undergraduate students coming to me. And for the first time I learned this word problem. as if there is something called word problem. I had no idea before that. Okay, because if you know the subject, you will apply it. That makes sense. The difficult part in the word problems, I mean, the related problems, is not so much the phobia, let's say, let's call it a phobia about word problems, but finding the relationship between the two primary variables. Here, it was very easy, a equal pi r square. But in some problems, that's the hard part. So you have to use algebra, trigonometry, some kind of geometry or something, or some other kind of thing to figure out the relationship between your primary variables. That would be the difficult job, many places. Many students cannot do that correctly. So I will do another problem just to show you, very easy problem. Okay, and the very easy problem says this one. We already did that, so we will not do circular. Okay, triangular shape, triangular bob. Yeah, some kind of swimming pool is filled with water. Okay, let's do the other problem. Say a boat is being pulled. Okay. A plane is flying at, say, at a certain speed, say 200 miles per hour speed. Okay. If I want 200 miles per hour, I want to make it even smaller, 150 miles per hour. And a height of, say, 2000 feet. So can you imagine the plane flying over your head at a speed of 150 miles per hour, but an height of 2000 feet? Okay. Okay, which I did not mention possibly, at a height of 20 feet, horizontally, flying horizontally. It's not going up and down, just flying horizontally. Okay. So we have this problem. A plane is flying at horizontally at 150 miles per hour speed and at a height of 2000 feet towards an observer. Find the rate at which the angle of elevation of the plane changes when the plane is a mile away. Okay, 1 mile away. It's not just 1 mile away from the point directly above the observer. So suppose you are the observer, you're standing somewhere on the ground. Okay, and the plane is flying directly towards you, but it will not hit you because it is flying at a height of 2000 feet. So when it is closest, it will still be 2000 feet above your head, you know. And you would like to know what is the rate at which the angle of elevation, because as it comes towards you, it looks higher and higher in the sky. When it was far away, it was down in the sky, you know, and then it's closing, it looks higher and higher towards you. So I would like to know what rate the angle of elevation changes when the plane is 1 mile away. There are two problems. First of all, you have to define the units, the variables, primary variables in this problem correctly. Also, there is a mixture of, you know, units. The unit is at one of them, some of them are given in miles, some of them are given in, okay, let's just make it 2200. Okay, just is that good? No, it's not good, not good. There's no need to do that. 2000 good is good enough. So there is a miles per hour, there is 2000 feet. Maybe know at what rate the angle of elevation is changing per second.
How many feet is a mile?
Yeah, that's what you need to know. Now, again, I repeat you this thing. If you, for instance, have any difficulty about what is angle of elevation, suppose you forgot, you're supposed to know that. Or how many feet in a mile, or how many seconds in an hour. You are expected to know, where people generally know these things, but you are not being tested on your knowledge of those things. You can ask me, I will tell you. I will tell you in a moment exactly how many, you know, how many feet in a mile. Okay. So suppose I change the problem, how the angle of elevation changes is changing per second. Let's just put it is changing per second when the plane is 1 mile away from the point directly above the observer. Okay, so actually there is 5280 feet in 1 mile. Okay, so I'm going to just write down that thing. 1 mile, not mole. 1 mile equals 5280 feet. Okay, also 1 hour equals 3600 seconds. What happened? See. Okay, so in case you didn't know this number, just ask me, I will tell you, because I'm not testing you on your knowledge of units. I'm testing you on knowledge of calculus. Okay, so let's just go put that problem. E go up. Yeah. So with this knowledge, for instance, we have to make it a picture. We draw a picture, which I will have difficulty drawing it here. I mean, I can draw the picture, but you know, chat. Will we use chain rule again? We are using chain rule. And we will be using continuously chain rule. Okay, even here, we are using chain rule. Here, when I use this formula, the di dt equal 2 pi r dr dt, that's chain rule. Didn't I? Because you are thinking, oh, this kind of problems I call chain rule, but this is chain rule. We are using, when we do related rate, you know the rate of one object, rate of change of one object, and you want to know the rate of change of another object. That's why it's called related rates problem. Okay. So what should be our primary variables? To do the problem, first we define the primary variables. So I'm going to draw a picture on the what's called whiteboard. Okay. Let's see. Draw a picture. So here is suppose our ground. Here is suppose the observer. Okay. So stamp text. Yeah, put some here, suppose. Observer. Let's call it O. Okay, so that's the observer here. And suppose the plane is flying on top, draw. Plane is flying like this way. So at any point, here is the point P, suppose. So I'm going to put the point plane, go up. Okay, plane. Call it P. So this line from joining for O to P is a straight direct line joining the observer to the plane. Okay, do you want me to drop good time? I will not be able to do that. Good picture of a plane going around. This is the vertical distance. As you see, this is the vertical distance, right? Which I'm going to draw also. What happened to our who are change of color, it's a format, etc. Okay, line width. Did I change the line width? I don't think so. I'm going to delete this. No, this is not the one. Okay, so draw. Now we got it correctly. Right. This is the angle. That's the angle of elevation. So remember, first of all, angle of elevation. Let me see whether you can see it. Oh, move it far away. Let me stand up. Let's see. Angle of elevation is always measured from the horizontal. Above, it's called angle of elevation. Is downwards. When you're looking downwards, is angle of depression. Okay, it's never the angle on top. Some people make a mistake. So angle of elevation is always measured from the horizontal. Up for the angle of elevation, down for angle of depression. Okay, so this is the angle of elevation here. This is the angle of elevation here. Eraser, erase this one. Yeah. So I'm going to make a kind of circle here. And that's our angle that we are interested in.
Would that be theta?
Yeah, you can give it any name. If you want to call it theta, theta. If you want to give it any other name, that's your choice. But suppose I'm going to give it the name. What happened to the O? I possibly erased that one. Yeah. O. What is this vertical distance? If you want to call this area, give it a name, Q. So PQ we know is 2000 feet, right? Although I should have drawn, could have drawn this thing, but this is changing. PQ is not changing. Theta is changing. Okay. PQ is fixed at 2000 feet. Plane is going towards. Yeah, you have to look at, you are right, possibly, Jonah. Let's see what we get, out of it. So since I have to go back to the page, draw this picture on your notebook, something like that. And I'm going to write down also, this is 2000. Yeah, this is here. 2000. And here we draw something, give it a name, say X, for instance. Okay. And this one we'll call theta.
Isn't that 1 mile X?
Pardon?
Isn't the X 1 mile?
Hang on just a moment. Let me just write down this thing. So suppose we call it theta for the moment, okay? The angle. Okay, that's all we need. And then of course there is the speed, etc. So draw this picture on your notebook somewhere, because I'm going to go back to our Word document. Okay. So draw this picture on your notebook. Okay, I can also draw an arrow. Can I draw an arrow? Not this one. What arrow? I need arrow. Let me see what happens if I draw something like this. No, it's no good. Erase it. Yeah, I want the arrow to go only one way. No, we don't have that. Okay, so I will draw this. Okay. So P is the plane, O is the observer, and Q is the point directly below the plane. I could have also drawn the Q here, which is the point directly above the observer. That could be also a good thing to do. Okay, but you're possibly more familiar with this kind of a picture. So I'm going to, close this one. I'm going to go back to the new share. Let me see, where is our new share anyway? New share, 7 class. So you can draw a picture, or you can say, here, suppose you draw a picture here, imagine that one. So we will define our variables correctly. So we'll say let x equals horizontal distance. From the observer. And we have to make a decision. Do we want to write everything in terms of miles or in terms of feet? I'm going for feet. Okay, but you can also write it in miles, everything. What else do we need? And theta equals it's a special character, right? Angle of elevation. Because they talked about angle of elevation themselves. I mean, whoever wrote the problem, namely me, it works out right. And time is t. Again, we measure time in minutes or seconds. I'm going to go for time, time t equal time in seconds. So we have to change a few things. Since I decided to go for, writing everything in feet, the 2000 feet height, no change. 1 mile is 5,280 feet. That's the horizontal distance. And 150 miles per hour. You can convert miles per hour into feet per second. So 150 miles per hour would be so you multiply 150 by 5,280. Where is multiplied here? 5,280. Then divided by 3,600. And when you do the calculation, you will get 220. That means 220 feet per second. So 150 miles per hour equals 220 feet per second. Okay, do the calculation, you will find 220. right? Check with your calculator. Now we need what we know. We know that the plane is flying at the speed of 220 feet per second. Okay, so we will say the dx dt. I have dx dt somewhere written here, right? Dx dt equals, let me see whether anybody can tell me correctly. Lale, what is dx dt? Is Lale here? Let me check.
Yes, I'm here.
Okay. What is dx dt? The dx dt is the rate of change of the horizontal distance. Because the plane is flying horizontally, right? So the rate of change of x is the speed of the plane. Correct?
Yes.
So you think is it 220 feet per second? Is it 220 feet? Shall I write 220 there?
I'm going to say yes.
It looks like it, right? Yeah. Let's go back. Somewhere here. Okay. No, it is negative. Be careful about that. It's negative. It's coming towards you. Okay. So it is negative 220, correct? Because the plane is coming towards the observer. Distance is decreasing. Correct?
Okay, that was tricky.
That makes
I
sense
wouldn't
to
have
you?
got that.
Yeah. I mean, without that, you will get a negative answer, wrong answer, in the sense that instead of angle of elevation increasing, you'll get an angle of elevation decreasing, which is not right. As the plane comes towards you, the plane looks higher and higher in the sky. What other thing we need to do is our two primary variable, x and theta. Okay, do I need to go back to the picture to look at the relationship between x and theta? That's why I asked you to draw the picture on your notebook, okay, on some paper, so that we don't have to go back there. So the vertical distance was 2000. The horizontal distance was x. X is changing. And the angle is this. So tan theta equals 2000 over x. Correct? 2000 was the vertical height and x was the horizontal distance, and tan is, opposite over, adjacent. That's what you call, right, in this country, right? So taking derivative with respect to time, so whenever we write with respect to, WRT, it stands for with respect to time. We are taking derivative with respect to time. Okay, we get this result. The derivative of tan theta would be sec square theta. Go back. Somewhere we must have sec square theta. Yeah, sec square here. Yeah. Sec square theta times d theta dt undo. It's confusing. Sec square theta times d theta dt equals derivative of the other side. We know the derivative of 1 over x is negative 1 over x square. If you have taken lots of derivatives, you know the derivative of x 1 over x, which is x to the minus 1, is minus 1 times x to the minus 2. So we can write down the answer in one line here. And then put something here and write the derivative of 2000 divided by, 2000 divided by x square. No, not that much, only this much. So the derivative of 2000 over x is negative 2000 over x square, the derivative of this with respect to x, times the derivative of x with respect to time, dx dt. Right? And we know dx dt. Do we know sec square theta? So we have to do work on this one. So at the moment, or at the time when the plane is 1 mile away, 1 mile was 5,250, 80. At the time when x equal to 5,280, first of all, tan theta. So that is 2000 divided by 5,280. Okay, you can simplify it, you can write in decimals, whatever you want to do, you get some number out of it. So if I get it in decimals, you know, we need to write the exact numbers whenever possible. So learn to use your calculator, use the answer button on your calculator. Okay, so when I need it, I will not divide by the decimal approximate value I'm writing here, but the correct number, 0.378787. Something, okay? Well, actually make it 88. 378788. And that's the value for 2000 over 5,280. But that's the actual value. Okay. Then sec square theta would be one plus tan square theta. And that would be equal to whatever we can write on your calculator, 1 plus answer square. Answer is just the number that is over the negative sign. So second negative sign and hit the square button. And that gives us 1.14348. Approximately, okay? That's the exact value is 1.143480257, but we are not write everything. So we got that number. We know dx dt is negative 220, right? So sec square theta, which is this number, 1.14348 multiplied by d theta dt equals, there is two negative signs coming up. Okay, so one is this negative sign times 2000 divided by x square. Okay, I'm going to write it in like that way. 2000 divided by x square. X square, x is 5280. Chat, what did somebody say? Okay. What value of theta did you use? I don't even bother to calculate the value of theta. I just wanted sec square theta. That's all I need. Okay, tan theta is this, so sec square theta is this. That's all I need. So I don't know what theta is. Divided by 5280 square. You can figure it out by using the arctan button on you. Tan inverse. Oh, sorry, my mistake. That's this. Okay, fine. Multiplied by negative 220. Okay, you can calculate this number if you like. Two negative signs cancel. We have 2000 multiplied by 220 divided by 5280 square. And we got 0.0157828, etc. Oh, you know, 157828, etc. 828, 8282, etc. 8283, suppose, you know. So that is what we got for this calculation. Then this is the dt would be whatever number we got divided by 1.143, this number, right? So divided by 1.143, etc. Okay, you can calculate that number. And we got 0.0138 something something. I'm just 0.24493, etc. Okay, I'm just going to write down this only. Well, if you like, you can write 0.24493 if you like. Okay, but we got this number, and unfortunately, that's not what we want. Do we? Are we getting that number? Yeah, because angular elevation changing at the rate of per second. Our time is in second, so we converted everything in second. So that is our answer. Okay, so that's our answer. So we will say at the moment when the plane is 1 mile away, the angle of elevation is changing, increasing, actually, more correctly. Angle of elevation is increasing. How are you doing that? At the rate of at 0.0138, and you don't have to write anything, per second. If you want to write per radian, so many radians, you can do that. But if you want to get the number in, you know, you can write down radians per second if you like, but you don't have to. If you don't write anything, automatically we will assume it is radians per second. Or in case you are interested, we can convert it into degrees per second. And the answer is 0.7908 or something. Okay, 0.79, that's good enough for us. Degrees per second. Degree of arc. .79 degree, about 1.8 degree, about 4/5 of a degree per second. At that rate, it will be coming towards you. So that's what we got, right? This is the level of difficulty that you will find in the exam problem. So ask yourself, what was the most difficult part of this problem? Was it understanding the word problem? Was it converting the units? Was it writing down what exactly is dx dt, what is dt, etc.? To make sense of it, read these problems, make sense of what they are talking about. How much time left? How much space left? I have 10 minutes left, or 8 minutes left, possibly, right? Let me check. Yeah, whatever it is. It is. My God. Oh, but lost something. What is it? This is CR1. No, we don't want that. No, it's not here. I'm just wasting time. Oh, it is here. Yes. So, also, when you get an answer, try to make sense of it. Does it make sense? Does it look like right? Maybe 1 degree, 2 degrees per second. Yeah, maybe 0.79 degrees per second. That's the rate at which it's coming. The plane was not flying very fast. It was not flying very fast. It was at only 150 miles per hour speed. Okay, typical jet planes fly at 4 times as much speed. So this could have been a much better answer that way. Okay, so we're going to go to a, say, enough, not enough space. Let's go back to this space. Okay. Oh, not here. Suppose the question is also, what is the rate at which the distance is changing? Okay. So suppose we also added what is the rate of change of the distance, direct distance between the plane of the, this times it is going to be OP in our picture, the hypotenuse. Okay. So if y equal distance, direct distance, okay. So let's copy from there. Distance between observer on the plane, we need some information about relationship between y and x. We can do it in terms of theta also. Because this time y equal 2000 times sec theta, right? And notice that I didn't even calculate sec theta because I needed sec square theta. That's all I needed. So I didn't even take care of, I didn't bother to take the square root of this number to get sec theta. I can do it that way also. I can also do it by using relationship between x and y. But let's do it the easy way. Y and relationship between y and theta instead of y and x. So y equals 2000 times, remember that 2000 times, is it sec or cosec? It's cosec actually. Wait a minute. Cosec theta, right, 2000 times cosec theta. Oh, this is that is increasing, right? This that is increasing. Where is theta? So I can write in terms of cosec theta if I like. Yeah, I thought it would be sec theta, so it didn't work very well. I can do yeah. I can either do this way or we can do the other way, is x square plus y, y square equals x square plus 2000 square. That would be good, I can also do it that way. So either I can get it in terms of theta or in terms of x, whichever is easier. Maybe that is easier for you. Let's just get rid of this one. Okay, we have y square equals x square plus 2000 square. I can put the 2000 in parentheses if you like, just to make it look easy for you. So from the, x is the bottom, I mean the adjacent side, 2000 is the opposite side, and y is the hypotenuse. Look at that picture that I asked you to draw. So taking derivatives, we get 2y divided dt, instead of taking derivatives of square root, taking derivatives with time. We get this thing. 2y times dy dt. Let's go back dy dt somewhere. Look for dy dt here. Equals the derivative of a constant is 0. So we get 2x times dx dt. And dx dt we have here somewhere, possibly here. No, not that, the full thing. Why is the dx dt? I didn't, yeah, here it is, dx dt. I wrote it down. So 2x times dx dt. So we have this relationship. Now, if I know x, I know y, I know dx dt, I will get dy dt. Okay, if you divide by 2y, if you divide by 2y, you get, or dy dt equals x over y times dx dt. Okay, So let me copy that one, dxdt. And then I'm going to write x over y in front of it. So here we go, put something. I think we are over time. Yeah, we are over time actually, 1 minute over time. Let me finish this calculation, and then you can, wherever you are, So we got this thing, divided equal xy divided. Do you want to continue on next, next time on, that is the Thursday. This is Thursday, right? So that would be Monday. I can continue this one on Monday if you like, if you do not want to stay any more longer. I'm going to stop share. Okay, and I will continue this one, or I will finish the problem and then send it to you by email. That may be preferable to you. Okay, stop recording. I might stop recording anywhere.